Good morning, everybody. How's everybody doing? I hope you had a wonderful, wonderful weekend. Um, and I hope you're enjoying the weather. I guess it's really cold outside. We have snow up here. So before we begin, I just want to remind you of a few things. So let me hop over to share my screen on my desktop here. All right. And let me zoom in as well because it's a little bit small. We have an exam this upcoming Friday. So please make sure you go through the study guide and practice some problems. You should also note that when you practice a problem, if you just skip to the end, or if you do a few practices and you maybe, I think there's 5 tries or something like that, when it regenerates, it'll regenerate a completely different problem. So each problem has actually a bucket of problems associated with it. So you can get more practice just by doing several versions of the same problem. Let's see. You have 7.7 that's due today, and 7.8 that's due on Wednesday. We have a quiz, not today, but on Wednesday for 7.7. Very short quiz, actually, but just to let you know. And I think that's about it. Oh, that's not about it. So we had a department meeting last Friday, and we were discussing Math Awareness Week, which is now. And actually, I'm not sure if it's right now. I think it's April. Anyway, doesn't really matter. The fact is, we're going to be holding possibly the integration bee this year. So we don't know exactly how we're going to do it. We're in the process of designing that. But I'm the lead on that. So we'll figure it out within the next 2 or 3 days, and then I'll let you guys know. If you want to participate in the integration bee, you are more than welcome to. It's normally a really, really good time. This time it'll just be a really good time. No double really on this one. So actually, I don't know. I'm hoping that'll be a really good time. But we have to figure out how that's going to roll in a digital online environment. This time next year will be fun because we'll be on ground again, but not this semester, unfortunately. So I'll let you guys know. The main thing to be aware of is it's likely going to be, or it's definitely going to be after spring break at some point. So there's still 3 weeks until the possible integration bee. If you want to join, you're more than welcome to. All right. So today we're going to step right into chapter 11. And I kind of previewed this last time, but now it's time to go through. I hope that you have the printed out lecture notes, or at least have access to the PDF, because I would not want you to write down all the definitions that we're going through today. It's just a lot of wording. So this I'm going to not power through, but I'll at least spend a little bit of time making sure that I see my screen on you guys can't see this, but my desktop screen is wacky right now. Anyway, you guys can't see this, or I'm sorry, you guys don't know this, but I'm not going to speed through, but I will kind of go a little faster than what will be comfortable for some people if you have not had a good rigorous course in Calc 1. If you had only Calc 1, the equivalent in high school, and then you assessed into Calc 2 in college, Calc 1 in high school does not have the same level of rigor that Calc 1 does in college, and so you've missed out on quite a few pieces that are important for Calc 2 and 3, that's just how it is. So I'll try to build that into this lecture. So the first thing we're going to start with is the layperson's definition of a limit of a sequence. This is how I start with a limit for a function, the layperson's limit for a function. However, when we do a layperson's limit for a function, and if you don't know what laypersons mean, it just means the general definition that you can kind of get away with a little bit, but it's not super precise. The layperson's definition for a limit was that the limit as x approaches a of f of x is equal to L means that we can make f sufficiently, or as close to L as we want, for x sufficiently close to a. So that was the layperson's definition of the limit of a function as x approaches a finite number a. I call that a finite limit at a finite point. In fact, I don't just call it that. It's actually called that. However, if you'll notice, when we talk about sequences, highlight that a sub n there. Excuse me. When we talk about sequences, our input, and in this case, is not going to a finite number, it's going to infinity. And that should make sense. If you have a sequence of values, a1, a2, a3, a4, and so on and so forth, really, when you're talking about a limit, you're basically saying, I need to know what that sequence tends to as n gets huge. So what does a sub 1 billion become, or whatever it is? So here we go. We say that the limit as n goes to infinity of a sub n is equal to L if we can make a sub n as close to L as we want for sufficiently large n. Additionally, we say that the limit of a sub n as n goes to infinity is equal to infinity if we can make a sub n as large as we want for all sufficiently large n. And again, the first one is saying we can make a sub n as close as we want to L. The other one is saying we can make a sub n as large as we want, because we're saying in this second limit situation that a sub n is tending to infinity. Visually, when you're thinking about sequences, they kind of look like this, where you have, let me draw an x-axis here. We'll call this 1, 2, 3, because if you've watched the videos to review sequences, you know that the difference between a sequence and a function is that most functions are defined over continuous domains, whereas sequences are defined over the natural numbers in general. So you have some value for your sequence at 1, and another value at 2, and another value at 3, and so on and so forth. And in this case, if you just think about the picture that I'm drawing here, it looks like as n goes to infinity, the value of the sequence is likely going to blow up to infinity. So this would be case 2, right? Case 1 could look something like this: 1, 2, 3, and 4, and so on and so forth. I'm not going to draw them all out, but that might be a sub 1. This might be a sub 2. That might be a sub 3. This might be a sub 4, a sub 5, a sub 6, a sub 7, a sub 8. So this looks like as n goes to infinity, that the sequence tends to a height of 0. All those dots tend to wiggle around 0 and eventually get as close as you want them to 0. So anyhow, that would be definition 1, an example of definition 1. This would be an example of definition 2. All right. So that's just a brief reminder of limits and the layperson's version of a limit. However, you can't get away from the precise definition of a limit of a sequence. So the precise definition is this from your Calc 1 class: the limit as n goes to infinity of a sub n is equal to L means that I think if you haven't had, well, if you haven't had Calc 1, then you'll need to understand what this is. The upside down capital A means for all, or for any, or for each. So for all epsilon greater than 0, the backwards capital E in symbolic logic means there exists. So for all epsilon greater than 0, there exists some value capital N, which is much greater than 0. That's what that double inequality means, much greater than 0. Such that, where's my such that? There it is. Such that as long as little n, now we're involving that little n, which is a subscript here, as long as little n, oh, by the way, it's also subscript there, is greater than that big N, that will imply that the difference between your sequence and your limit is less than epsilon. Now, it's likely been a while since you've seen that rigorous definition, so let me go ahead and give you a visual very quickly on this. Let's suppose that we have an x-axis, And let's suppose that as n goes to infinity, we're saying that our sequence is approaching a height of 5. Let's pretend that I'm going to draw actually a horizontal line rather than dash it out, but let's pretend that our sequence is approaching a height of 5. So let me draw in a y-axis as well. And I'll label all these. That way it's really easy for you to see. There's the y-axis. Right down there, that's the x-axis. And in green, that green line is a height of 5. And let's pretend that we have the sequence that is supposedly reaching that height of 5. I'm going to do the sequence in red just to really kind of make it robust, I guess. It doesn't always need to be above that line. I'm just making it easy for myself here, because it could alternate back and forth like I did in that previous example. Okay, that's good enough. All right. So I'm claiming that that sequence of points that goes on forever, by the way, I'm just only limited it right now just to those few, but it goes on forever. And I'm claiming that the limit as n goes to infinity for that sequence of points is equal to that height 5. So the claim is that the limit right here, that the limit as n wanders off to infinity of a sub n is equal to 5. That's what I'm claiming. So the true definition, or the precise definition of a limit, tells us that for any epsilon neighborhood somebody gives me about y equals 5. So I'm going to draw that in blue, that somebody hands me an epsilon neighborhood. Let's pretend the epsilon neighborhood is this size right here. Let me go ahead and do it on either side. There we go. I'll turn that off. Okay. So again, remember, the screen value is a height of 5. This will be 5 plus a wiggle of epsilon. This will be 5 minus a wiggle of epsilon. And the claim is that for any given epsilon, in this case, I gave you somewhat of a large epsilon neighborhood, a large wiggle about 5, we can find a value of n on the x-axis. And I will pretend as though that value of n is right here, capital N, such that for all x values greater than that, or for all n values, little n values greater than that, their corresponding sequence values land in that little epsilon neighborhood. And you can see that from that point forward, all those little sequence dots here land within those epsilon bars. And that is just a reminder of that definition. It's the precise definition of a limit, of an infinite limit, a finite limit at infinity is what that one is. But anyhow, so this is the precise definition of a limit. We won't be actually diving too much into that. One, because it's a prerequisite for this course, but two, because you just don't use that definition that much in Calc 2. So you do use it every once in a while, but it's an incredibly rare circumstance where you use it. So don't get freaked out too much that you have to be like awesome with that. It still is important to remember. It's assumed that you know it. Anyhow, that being said, let's go ahead and talk about the language of sequences, and specifically limits of sequences. And this language will include some of the language we just introduced ourselves to with improper integrals. So convergent and divergent sequences this time, rather than improper integrals. So if the limit as n goes to infinity of a sub n exists, just like in that last example for the definition, as n went to infinity, we saw that those dots were tending to a height of 5. So if it exists and is finite, then we say the sequence converges. Otherwise, we'll just say that the sequence diverges. Pretty easy. So if a sequence as n goes to infinity becomes a finite number, it's convergent. Otherwise, it's divergent. A great example of a divergent sequence is, let me draw in an axis here. It's very simple divergent sequence is the following sequence. A sub n is equal to -1 to the nth. That's a divergent sequence because when n is equal to 1, the value of the sequence is -1 to the first. When n is equal to 2, the value of the sequence is -1 squared. When n is equal to 3, the value of the sequence is -1 cubed, and so on and so forth. So as time goes on, this sequence just bounces back and forth between 1 and -1. And because it doesn't become finite as n goes to infinity, we call this a divergent sequence. Excuse me. So because it doesn't become finite, it doesn't like converge to something, it is considered to be divergent. Even though those two values, 1 and -1, are finite values, you can never say, oh, well, as it goes on forever, it's just 1. It's not. It's 1 or -1. So because it's not something, a singular something, it is divergent. All right. So that being said, again, it's like a whole beginning of every chapter is a hodgepodge of definitions, really, just to get you into the newer material. All right, but here goes our first theorem. So given a sequence, a sub n, and a function, clicking on something off to my right-hand side really quickly, and a function f sub n, or f of n, which is equal to a sub n for n in the natural numbers. If the limit of your function is L as x goes to infinity, then the limit of your sequence becomes that same value of L. Now, let me read this again. And this time, as I read it, I'm going to go ahead and draw a picture. So let's suppose somebody gives me a sequence that matches a function for every natural number. So for example, I have, let me get my ruler out again so that I can at least draw in a picture here. So let's pretend as though we have a function. We'll start with that. It's a little bit easier to say that. And my function, let's say my function looks like this. So as x goes to infinity, it looks like my function, excuse me, is tending to a height of 0. Okay. So this is the limit as x goes to infinity of f of x, and we're going to say that that is actually equal to 0. Let's just pretend. Now let's pretend as well that we have a sequence that matches the function at all natural number values. So in other words, at x equals 1, my sequence lands on the function. At x equals 2, actually, let me draw in all the natural numbers first, because otherwise I have to hop back and forth between inks. Just need to quickly do this. I will say that's 9, 10, 11, 12, and you get the idea, right? 13, and we'll just go up to 14 because 13 is bad to stop at. All right. So let's say that we have a sequence that at all the natural numbers, it ends up having the same value as the function. So these red dots are the sequence values. Scrolling over here. You can tell those red dots are also eventually, because they match the function, they're eventually going to limit to 0 as well. And that is what this theorem is saying, is that if you have a sequence that matches the function at all the natural number values and the limit of the function becomes finite and L, so this is some value, I just chose 0 in this case, then your sequence will also limit to the same value. That's exactly what this is saying. A little bit of a warning. The converse of this is not true. What do I mean by that? Well, that is the limit as n goes to infinity of a sub n being finite does not imply that the limit of the associated function as x goes to infinity is that same finite value. And there's a very simple example to showcase why these two, why the first, the limit of the sequence being finite, does not imply the limit of the functions being finite. And that visual is, again, very easy to see once you draw something out. So let's suppose that I have a sequence that looks like this. So I'm going to plot red dots for my sequence value. I have to be kind of careful. These should be equally spaced. Now, I hope you would agree that because these sequence values are all the same height, that obviously they would converge to whatever that height is. So let's say that height is a height of, oh, I don't know. Let's say it's a height of 1. Okay. So that sequence that will go on forever and have that same pattern looks to converge to a height of 1 because it's always a height of 1. However, just because that sequence converges does not mean that the associated function that that sequence touches converges. For example, the function could be, I'm going to draw this kind of terribly, the sine curve. I mean, that's a terrible sine curve, but I kind of missed it right there, but oh well. But the associated function as x goes to infinity does not converge. It keeps bouncing back and forth between -1 and 1. So sequences are more likely to converge than their associated functions. However, if you know the associated function converges, then you know the sequence converges. So the convergence of the function, I guess I'll call that the moral of the story. That's what I'll call that. It's the moral of the story. If the function converges, the related sequence converges to the same value, actually. I'll just put that last statement in parentheses. But the convergence of the sequence says nothing about convergence of function. There we go. So that's the moral of the story. If the function converges, the related sequence must converge to the same value. But the convergence of the sequence says nothing about the convergence of the function. There we go. I'm going to mute myself so I can take a drink and clear my throat too. Okay, so let's go ahead and prove this theorem. Now, the theorem says, given a sequence and a function. So we're going to start with that. The proof is actually pretty quick. I'm just going to do it this way, proof. So given a sub n and f of x, so we're given a sequence and a function where f of n, when you plug in a natural number to the function, it ends up being the sequence value. Okay, so that's part of the piece where we can assume, because that is the antecedent, not the consequent. Oh, and that's for n in the natural numbers, all right? So let's suppose that our function converges to some value L as x goes to infinity. Well, I should make that little note here. Okay, there we go. Okay, suppose the limit of the function as x goes to infinity is some finite number L. Well, then by the precise definition of a finite limit at infinity, we know the following. For any given epsilon that somebody comes into the room with and hands us, there must exist some number n, and it's likely going to be very large because the number that we have to find is all about the x value. So there's likely some large number n such that as long as x is greater than that large number n, that will imply that the difference between our function and our limit that we're trying to get our function to approach is very small. How small? Well, that distance between those two things, the function and the limit, is so small, it's actually smaller than the very small number epsilon that somebody walked in the room and handed me. So basically, I'm squeezing the function and the limit together as x goes to infinity. And I mentioned that x goes to infinity because x is greater than some huge value of n that we're going to find. We actually don't need to find it in this case, but that's the statement. So again, suppose we're given a sequence and a function where the function matches the sequence value for all natural numbers. And we're also going to suppose that the limit of our function is finite as x goes to infinity. Well, by the definition, precise definition of a finite limit at infinity, we have this statement here. Now, every good mathematician has scratch work. You don't just run through a proof knowing exactly where you're going. So off to the right-hand side, I'm going to start some scratch work so I can figure out how I'm going to do the rest of the proof. I'm going to look at what I want to arrive at. Let's see, we've already written down all of this stuff. All of this stuff we've written down, even this stuff right here. So all of that is done. I need to prove this last little bit, that the limit as n goes to infinity of a sub n is equal to L. So I'm going to go ahead in my scratch work and just say, I want to show that the limit as n goes to infinity of a sub n is equal to L. So here's my scratch over here. I want to show that the limit as n goes to infinity of a sub n is equal to L. Now, that means to me that I need to somehow say that for any given epsilon, because this is a true definition of a limit of a sequence, I need to say that no matter what epsilon somebody hands me, I can find some very large value of n. Now, notice this blue ink exactly matches my black ink right here. So this is really fortuitous. It's very, very beneficial for us because we can kind of use everything we've written in black. But let's see what else we need. So for any epsilon greater than 0, there exists an n greater than 0 such that little n being greater than this big N should imply that the distance between my sequence and my limit is less than epsilon. Okay. Well, most of that is actually written in black over there. In fact, the only thing I really need to trade out are n's. So it looks like, I'll write it here. Looks like I need to trade little n for x. Let me just double check that. If you look at the black ink over on the left, this x right there, that n right there, they're in the same spots. So I need to trade out little n for x. And if you notice within the absolute values, f of x should be traded out for a sub n. So I'm going to go ahead and make that mention too. And let's see, a sub n for f of x. So then you start thinking about, how am I going to do that? Well, the easiest way to do that is to use the information they've given us. So note, I'll just say it right here, note that f of x is equal to a sub n if x is equal to n. That's just from this statement right here. F of x is equal to a sub n if I replace that x with an n. So f of n is equal to a sub n. So letting x equal n in our definition here, we get, for all epsilon greater than 0, there exists some capital N much greater than 0, such that, normally I don't write out such that, I have symbolic language for that too, but I'm not doing that here. Little n greater than big N should imply, again, because we're letting x equal little n, implies the absolute value of f of x. But remember, f of x turns into a sub n if x is equal to n. Well, x is equal to n here, so f of x is going to be traded out for a sub n. And by definition, that is, by definition, this is the limit as n goes to infinity of a sub n is equal to L. And that's it. That's the proof. It's very short. We've proven that if the limit as x goes to infinity of f of x is equal to L, then the limit as n goes to infinity of a sub n must equal L. It's always nice to have a proof. Start the day with a proof. That's what I say, especially right after Pi Day. It's a good day to have a proof. Pi Day was invented by mathematicians to sell more mathematics. All right. So let's go ahead and move forward. And people get very concerned. Do I have to prove that? It's not that you have to prove that. It's that as you move forward in mathematics, you have to engage with proofs more often. The level of thinking has to be kind of around there. So very important to note. Since we know now that limits of functions and limits of sequences are very related to one another. If your function converges, then your limit, then your sequence based upon that function will also converge, all that fun stuff. Then we can start pulling in all the properties of limits that we built. Sorry, I'm moving my camera over. That we built. No, I don't like it there. So right here. Let me see if I can't do that. Oh, well. We're going to pull in all the theorems that we built using the limit laws. So here are the properties of limits, normally for functions, but we're changing them to be properties of limits for sequences. And I wrote them out in language, which most people do not like. So I'm going to write them out symbolically as well so that you can see what each of these means. So the critical component here that your Calc 1 teacher should have focused on is if both of your limits become finite, then the following holds. The limit of a sum is the sum of limits. What does that mean? It means the limit as n goes to infinity of a sub n plus or minus b sub n. Well, as long as these are both finite, when you break them apart, that would be the limit as n goes to infinity of a sub n plus or minus the limit as n goes to infinity of b sub n. That is, the limit of a sum or a difference of sequences is equal to the limit the sum or the difference of the limits of those sequences. Hard to say. Again, you can only pull these apart if these sub limits are finite and exist. Now, that should sound very familiar because that's the same thing we said about improper integrals, that you can pull an improper integral apart, the integral, let's say, from negative infinity to positive infinity of something. You can pull that apart into two integrals only if both of those integrals converge. So that same statement, because it's based on limits, holds here. All limits kind of have that property. Property 2, the limit of a constant multiple is a constant multiple of a limit. That just tells us that if you have the limit as n goes to infinity of some constant times a sub n, you could factor out the constant. That's all that's saying. The third one, the limit of a product is the product of the limits, is very much like number 1, but with a multiplication sign. And actually, you could do that with the division sign. So 3 and 4, I'm going to glue together. Well, I guess I can't symbolically, so I'll have to keep them apart. Limit as n goes to infinity of a sub n times b sub n. As long as those sequences tend to something finite as n goes to infinity, then you can break these apart to limit as n goes to infinity of a sub n times the limit as n goes to infinity of b sub n. And we have one for the quotient, which I'm not going to bother with actually. But number 5 is the limit of a power of a sequence is the power of the limit, provided that the sequence is positive and the powers are positive. So actually, the powers don't have to be positive there. I don't know why that is written that way. That's just saying this. The limit as n goes to infinity of a sub n to some power p is the pth power of the limit as n tends to infinity of a sub n. And the power can be negative. So ignore the this condition. I'm going to actually erase that secondary condition there. No need to have that. The condition that the sequence has to be positive is because your power could be a 1/2 power. And if it's a 1/2 power, that's a square root. And you'd have problems if your sequence was negative underneath a square root. So that's why the requirement there is sequence has to be positive. So these should be familiar somewhat from your Calc 1 course. It's a whole like 2 sections of Calc 1 on limit laws. So, and then a whole chapter on limits itself. There's no need for me to prove any of these because these should have been proven in Calc 1. So I'm not going to bother here. Also drawing in from Calc 1, everybody's favorite theorem, the squeeze theorem. This is an awesome theorem. The squeeze theorem for sequences holds just like the squeeze theorem for functions. It's a very entertaining theorem. I'm going to color code this so you can see this. Notice I don't have the word proof here because there's no need to prove this one. Well, I don't want to say there's no need. It's a very difficult proof, even for the function. Proving the squeeze theorem for functions, that's an incredibly difficult proof. So let's suppose that you have 3 sequences, A, B, and C. And C happens to exist between A and B. Not always, but for some point. At some point, C is between A and B. So I'm going to do C in red here, just so you could see it. We'll do C in red here. So let's just say it looks something like this. Let me zoom out so I can at least get it somewhat properly spaced. Okay. Oh, and by the way, we're going to infinity, so let me make sure. Okay. So let's say that that's the sequence for C. And then A, I'll do in green. Be kind of careful about this. So A, I'll say it looks like this. Okay. And then B, I'll do in blue. Let's do it like this. And let me get that green in there too. All right. So what is this saying, this theorem? Well, if we happen to know that the limit as n goes to infinity of a sub n, which is our green here, if that limit ends up being the same thing as the limit as n goes to infinity of b sub n, some value, and notice on our picture here, the blue dots and the green dots are tending to get closer to one another as time goes on. Okay, so the blue dot, let's say the next blue dot is here, and the next green dot is really close to that. Okay, let's just suppose they're getting closer to each other. And if you happen to know that the red dots eventually are always between the green and the blue. So notice the red dot starts between the green and the blue, but it's not here. Well, that doesn't matter. What matters is that eventually the red dots are always between the green and the blue dots. And you can see that that's exactly how I designed this, that as time goes on, the red dot is always between the green and the blue. And let me go ahead and just put a little red dot right there. Then, because we know the green and the blue dots converge to something together, and because the red dot is between them always, at least after some point, then the limit of the red dot sequence has to be the same value as the limit of the green and the blue dot sequence. That is, if the upper sequence converges to the lower sequence, the one in between has to converge to the same value. It gets squeezed. And that's the squeeze theorem. A really cool theorem. And that does become very useful as we move forward in this section, in this chapter, sorry. So all your Calc 1 comes into play here. Let's see. I'm just wrapping up all the sequences and all the definitions and theorems here. So sometimes we're given a sequence that cannot easily be written as a function. In this case, the following theorem might help. So this theorem is often something that throws people off because they think that it's saying something it's not. So let's go ahead and dive into this a little bit here. I'm just kind of getting my my language set up. Hold on a second. I'm clicking something on my main screen, which is not working for some reason. Give me, oh, yeah, it is working. Okay, so what does this say? If the limit as n goes to infinity of the absolute value of the sequence tends to 0, then we know the limit as n goes to infinity of the original sequence is 0. And that's going to be somewhat powerful. It's not going to be like awesomely powerful, but it can be incredibly helpful at times. So let's go ahead and see the proof of this. And I'm just kind of bringing it up here. Oh, I have a couple warnings, by the way. This theorem only works if the limit is 0. That's incredibly important. So if you know that you have a sequence and you want to showcase that sequence limits to 0, sometimes it's just much easier to talk about the absolute value of the sequence and say the absolute value of the sequence tends to 0. Therefore, the regular sequence tends to 0. That's perfectly fine. But if the absolute value of the sequence didn't tend to 0, let's say it tended to 1, then you cannot say anything about the regular sequence. You cannot say, oh, therefore the regular sequence tends to 1. That's not true. That is totally not true, because your regular sequence could be bouncing back and forth between 1 and -1. Its absolute value would always be 1. So just because the absolute value of the sequence tends to 1 does not mean the actual sequence itself is tending to 1. The sequence itself could be bouncing back and forth between -1 and 1. So turns out that this theorem only works if the limit is 0, which makes it somewhat of a limited theorem, to be honest with you. It's a little bit confining. A little interesting note, technically, this theorem is a bijection. It's an if and only if. So in other words, it is true actually that if your limit of your sequence tends to 0, then the limit of its absolute value must tend to 0. And if the limit of the absolute value tends to 0, then the limit of the sequence tends to 0. However, we do not, or we rarely use this direction, going from the limit of the sequence being 0 to talking about the limit of the absolute value. We almost always go forward with this statement. So that's why we don't write as an if and only if. The proof of this is actually not too bad. We're going to use a simple fact here. So here's the proof. Note that we want to prove that the limit as n goes to infinity of a sub n is 0. So I'm going to start with bounding a sub n. I hope you would agree that a sub n itself is between the absolute value of a sub n and the negative absolute value of a sub n. Think of any number. It's between itself, the absolute value of itself, and the opposite of the absolute value of itself. For example, 3. Well, that's definitely between the absolute value of 3 and the negative absolute value of 3. Totally is. Same thing with negative 3. Negative 3 is between the absolute value of negative 3 and the opposite of the absolute value of negative 3. So it is true that any number is bounded between its absolute value and its negative absolute value. Let's assume that the limit as n goes to infinity, this is the antecedent, we're assuming that the limit as n goes to infinity of the absolute value of a sub n is equal to 0. So let's go ahead and assume that. All right. Well, if that's the case, just using the squeeze theorem, we can say the limit as n goes to infinity of the opposite of the absolute value of a sub n, well, that should also equal 0. That's pretty simple. If the limit of absolute value of a sub n is equal to 0, then the limit of the opposite of that should also be 0. Hence, by the squeeze theorem, and I'll just write ST for squeeze theorem, this limit tends to 0, that limit tends to 0, thus the central limit must also tend to 0. There we go. That's it. Very short proof. Very nice proof, actually. So there we go. We're going to use that possibly. I only use that theorem if I have a sequence that's bouncing between negative and positive values, and I just need to showcase that sequence tends to something finite, specifically 0. And again, this theorem only works if your sequence tends to 0. Take a drink real quickly. All right. So now all this theory out of the way. Well, let me just double check. Okay, you're good. We have one more theorem, and I like proof easy and only if we have time. I'm probably not going to prove this one, honestly. I think it might be even a homework question. All right, the sequence r to the nth, n starts at 0 and goes to infinity, converges if the common ratio, that should remind you of sequences and series in your pre-calculus course, if the common ratio r is between -1 and 1. The only difference between sequences and series in pre-calculus, in geometric series in pre-calculus, and this sequence right here is that in pre-calculus, we required that r, the common ratio, is between -1 and 1 inclusive. In other words, it didn't include 1. However, we can include 1 here because if r is always 1, you have 1 to the nth, which is 1. And you're going from 0 to infinity. Well, you just have a sequence of points, 1, 1, 1, 1, 1, 1, 1, 1, on forever. So it converges to 1. It's always 1. If that base of that exponential is between -1 and 1, then it's a fraction, a proper fraction between -1 and 1. And so as you power it up, as time goes on, as the power goes to infinity, that will shrink that number down to 0. It'll converge to 0. So that's what that last sentence is. Moreover, this limit is 0 unless r is equal to 1, in which case the limit is 1. So this sequence converges if r is between -1 and 1, or if r is equal to 1. Otherwise, it will diverge. That will be an important theorem. That's, again, it's technically from your Calc 1 and your pre-calculus course, but it was written in terms of functions at that time. In your pre-calculus, or sorry, in your Calc 1 course, you saw it this way. Limit as x goes to infinity of x to the p power. Well, if that power is greater than 1, then, or sorry, if the if the power is greater than 1, like 2, then as x goes to infinity, you have like infinity squared. That's just going to blow up. But if it that x, or sorry, if, well, in this case, that doesn't work out. Oh yeah. No, that's the problem. That doesn't work out. That's not what I'm saying here. I'm going the wrong way. Sorry about that. X goes to infinity, we'd have some base to the x power. Sorry, I was going the wrong way with that, because the variable, the thing that's moving here, is the n. Confused myself. All right. So if the base were greater than 1, right, then you have something like 2. Well, 2 to the x power is x goes to infinity will blow up, right? That gets massive. If the base was 1, well, 1 to the x power is always 1. Always. So that limit would be 1. And if you have a base that's like a half, let's just pretend it was a half. Well, a half to the x power, where x is getting huge, think of 1/2 to the 10th power. 1/2 just to the plain old simple 10th power, that's 1 over 1024. It's a really small number. As that power gets larger, the number gets smaller. So again, if your base is a fraction less than 1 in magnitude, that will shrink down to 0 as time goes on. So that's kind of the same thing from your Calc 1 course, just this time in terms of sequences. All right, all of the definitions and theorems out of the way, let's start using this stuff. So computing limits of sequences. You will see that the examples I choose here are somewhat higher level examples, because I'm not going to ask you silly things like, what's the limit as n goes to infinity of 1 over n? That's too easy. This at least involves sort of the same question, but has your your Calc 1 skills involved. So we want to know, does this sequence converge or does it diverge? If it converges, let's find its value. So we're going to need to take the limit as n tends to infinity of a sub n. We want to know, is that going to be a finite number, or is that going to be not finite? Let's go ahead and trade a sub n out for what they told us a sub n is. Let's see, that's 1 plus 2 over n to the nth. Now, here's something I've gone back and forth on over the years, but really, because n is not a continuous variable, it's a discrete variable. In other words, n is 1, 2, 3, 4, or 5, or so on and so forth. But it's not like 1.5 or pi, right? It's not a continuum of numbers. It's discrete dots. 1, 2. It's the natural numbers, right? Because of that, working with this limit notation is going to be very difficult. However, we have a theorem. And the theorem is, if we can create a related function to this, and if that related function converges, then this sequence will converge. Let me write that down. I'll say all of our, get closer in, all of our limit work, limit theory, is based upon functions. Right now, we're about to take the limit of a sequence. I would like to exchange that sequence out for a function. So let's swap this sequence out for its related function. So I'm going to focus, right? I'm not going to say this is equal to, because it's not. But what I'm going to do is I'm going to look at the related limit of the related function. So that means I'm looking at the limit instead of as n goes to infinity, I'm looking at the limit as x goes to infinity of, instead of 1 plus 2 over n to the nth, it's 1 plus 2 over x raised to the x. And what I'm going to do here, now I can just use my Calc 1 because my Calc 1 is based on limits of functions. I'm going to go ahead and use the theorem that we introduced very early on in this material. Let's see if I can find it. Yeah, that's this one right here. If the function converges, the related sequence converges. So that's the theorem I'm going to use here. This guy right here that I've highlighted and put a bunch of colors on and stuff like that. I have a related function. I want that function to converge, the limit of that function. If it does, then the sequence has to converge. Remember, the convergence of the sequence tells us nothing about the convergence of the function. Not that that will ever be an issue, but I'm just telling you that. So let's go ahead and go back to this problem we just started to work on. I'm going to see if this related limit of this related function converges. And I chose this for a very specific reason. Some people know this value immediately as e squared. However, I just want to showcase how you would get to that using your good old Calc 1 skills. So this limit as x goes to infinity is going to tend to 1 to the infinite power, right? That's 1 plus 2 over x, which is as x goes to infinity would be roughly 1 plus 0 raised to the infinite power. That's an indeterminate form. And because it's indeterminate, 1 to the infinite, you don't know what that's going to become. You cannot determine it. You're going to have to use some type of manipulation. And the manipulation I'm going to use here is writing or using this theorem. Let's see, b to the power p, all right, is the same thing as the natural log, actually, as e to the natural log of b to the power p. That's a theorem from algebra 2, right? So we know that if you have a base to a power, that's the same thing as e to the log of that base to a power, because e and natural log cancel each other out. They're inverse functions. So they'll undo each other and you'll just end up with that b to the power. So I'm going to trade out this blue limit for a limit as x goes to infinity of e to the natural log of 1 plus 2 over x raised to the x power. And that is solely so that I can pull that power of x out of this and in front of the natural log using my good old algebra skills. So I will write this as the limit as x tends to positive infinity of e to the x natural log of 1 plus 2 over x. Now, I didn't make a big stink of this in my calculus courses, but your instructor might have. So you can move this limit into the exponent because the base does not rely upon x. So I'm going to do that here. I'm going to say this is e raised to the limit as x goes to infinity of x times the natural log of 1 plus 2 over x. And now looking at this limit, I can see that as x tends to infinity, this piece right here will obviously tend to infinity. This chunk in here will tend to 1. And the natural log of something tending to 1 is something tending to 0. So this whole entire picture right here is tending to 0. And as I tell my Calc 1 students, 0 times, when you're dealing with calculus and limits, 0 times something is not always 0, because that's not, this right here is not necessarily 0. It's something approaching 0, and it's being multiplied by something approaching infinity. And they might offset one another, or they, that natural log might be approaching 0 faster than x is going to infinity. And so this will become 0, or vice versa. X could be tending towards infinity faster than the natural log is tending to 0. And so this would go to infinity. So there's a lot of ifs here. The only way that you could deal with this is to write it in the indeterminate form, either infinity over infinity or 0 over 0. Then you would be able to use L'Hopital's rule. In this case, I'm going to write it as 0 over 0 because you can use a little bit of a trick here. Let me get my red ink off of this so that you can see my trick. It's not my trick. It's the standard trick. So we had e to the limit as x goes to infinity. I'm going to keep the natural log in the numerator. And I'm going to write x that was right here. I'm going to pull it into the denominator. But if I do that, it's going to be called 1 over x. 1 over x is the same thing as x. So these are the same statements. But now that I've written it that way, as x goes to infinity, this denominator is tending to 0, and the numerator is also tending to 0. And now I can use L'Hopital's rule. Using L'Hopital's rule, we get e to the limit as x goes to infinity. L'Hopital's rule is the derivative of the numerator divided by the derivative of the denominator. So the derivative of the numerator is 1 over 1 plus 2 over x times, by the chain rule, a negative 2 over x squared. The derivative of the denominator is negative 1 over x squared. Multiply both numerator and denominator by a negative x squared. In fact, let me write that in there. I'm going to multiply top and bottom by a negative x squared so you can see my logic. Well, the denominator is nice. It just becomes 1. The numerator becomes a 2 over 1 plus 2 over x, which is super duper nice because as x goes to infinity, this little piece right here tends to 0. And we have 2 over 1 plus 0, or 2. And so this is going to equal e to the second. And as I said from the get-go, some people will look at this and they'll know that's just e squared. It is just e squared, but you still need to know how to use L'Hopital's rule for other problems that aren't that obvious. So the limit of our function, our related function, tends to e squared. That means by the earlier theorem, the limit of the related sequence also tends to e squared. We've done all the work on the right-hand side, so I'm just writing the result right there. So it converges to that. There we go. So that's a good limit problem for sequences. You could tell that you're going to have to dip into your bag of tricks for limits from Calc 1 very often in this chapter, actually. Take a drink here. All right. So if you have questions, please ask. But that's our first example of computing a limit of a sequence. Let's see if we have some more interesting examples. This is a really neat example, actually. Determine whether the sequence converges or diverges. If it converges, find the limit. Again, and in fact, almost always, I am going to, instead of working with the sequence, I'm going to trade it out for a function and find the limit of the related function. If the limit of the related function becomes finite and converges, then the limit of the sequence will do the same to the same value. So let's go ahead and let f of x equal the quantity x plus 1 to the 1/2 minus x to the 1/2, which rarely do I trade out half powers or rational exponents for radicals. But in this case, I'm going to help us see what we're going to do. So let's consider the limit as x goes to infinity. So I'm just looking at the limit of the function that's related to the sequence, because if that becomes finite, then the limit of the sequence will become finite. And instead of writing it as x plus 1 to the 1/2 minus x to the 1/2, I'm going to write it as the square root of x plus 1 minus the square root of x. Now, if you take a look at that, right as written, that is of the form infinity minus infinity. Again, an indeterminate form, because you cannot determine what this limit will be. A lot of people will say this is 0. Actually, it is 0. But a lot of people will say it's always 0. It's not always 0. So it just depends on which one's going to infinity faster. In this case, they're both going to infinity at the same speeds, so they will cancel out, but that's not enough to justify. So you have to justify it by multiplying numerator and denominator by the conjugate. Welcome back to Calc 1, right? So here we go. This is the limit as x goes to infinity. Multiplying numerator and denominator by the conjugate, we get x plus 1 minus x over the square root of x plus 1 plus the square root of x. Simplifying that numerator, doing algebra before calculus here, we have limit as x goes to infinity of 1 over root x plus 1 plus root x. Now you can see as x goes to infinity, you'll have 1 over infinity plus infinity, which is going to be 0. Because the limit of the function as x goes to infinity tends to something finite, specifically 0, the limit of its related sequence has to also tend to 0. So I'll say thus, the limit as n goes to infinity of a sub n, which was the c sub n, sorry. C sub n must also equal 0. It converges to 0. There we go. So that one was actually a lot faster just because it's just a little bit of algebra. Notice I'm trying to lean on my algebra as much as possible because, well, you want to do that before you go into anything else. All right. Well, let's go ahead and, if there are no questions, hop forward a little bit into something that you could not do with a function. You could not do this. You couldn't investigate this using Calc 1. It just won't happen. So, at least as written, determine whether the sequence converges or diverges. If it converges, find the value. There's no such thing as a function of the following form. F of x is equal to 2x minus 1 factorial over 2x plus 1 factorial. That's supposed to be a plus 1. My ink is going wacky right now. The reason why there's no such thing as a function like that is because factorials only, for our purposes, exist over the natural numbers. But when you have a function, generally speaking, functions are not limited to just natural number inputs. So this functional form is not going to work for us. When somebody says f of x is equal to, I immediately do not say to myself, oh, make sure you only plug in natural number values for the domain. Like, nobody's going to guess that. So this is a no-no. We don't want to use this. Also, we've just never taken a limit of anything involving factorials before. Oh, and it probably begs the question, if it's been a while for you, what the heck is a factorial? So a factorial, like k factorial, is just the product of this number and all natural numbers below it. So it's k times k minus 1 times k minus 2 times k minus 3, and it goes on and on forever, all the way down to 2 and then to 1. So for example, 3 factorial is 3 times 2 times 1. Also, a little bit of a heavy side note, 0 factorial is defined to be 1. That's very important. That triple equality means defined. So 0 factorial is defined to be 1. It's just important for other theoretical purposes. So there you go. Anyhow, so that's just to remind you what a factorial is. So if I'm facing this and I can't exchange it for a function, but I need to find its limit, well, I'll start by saying, what's the limit? I'll just write that in there. The limit as n goes to infinity of e sub n is the limit as n goes to infinity of 2n minus 1 factorial over 2n plus 1 factorial. Now, I haven't actually started the calculus, and I have some opportunity right now to not start into calculus. Instead, I would like to do some algebra here. And the algebra I'm going to do is factorial stuff. So the numerator, I'm going to leave that for right now as just a 2n minus 1 factorial for a very specific reason. And that is because the denominator is 2n plus 1 times, then I'm going to subtract 1, so 2n plus 0, times 2n minus 1 times 2n minus 2 times 2n minus 3 times 2n minus 4, and so on and so forth. So notice that this will simplify. It simplifies down because the 2n minus 1 factorials will cancel beautifully. And now our limit is somewhat obvious. This is the limit as n goes to infinity of 1 over 2n plus 1 times 2n. This one I don't really need to exchange out for a function. I'm okay if you don't either, because you know 1 over infinity, well, that's going to be 0. So with factorials, you want to use those properties of factorials. You actually want to do a little bit of algebraic cleanup before you deal with factorials like this. All right. So let's go ahead. Again, if there's no questions, I keep looking up in the chat to see if there's a question, but there's no questions. So let's deal with this bad boy. Notice all the instructions are the same. Determine if it converges or diverges. If it converges, find the value of the limit. In this case, this is going to use one of the theorems we wrote down earlier. If you think about this, as n goes to infinity, there's a lot of unknown things, weirdness is happening here. For example, cosine as n goes to infinity. Remember, you're plugging in natural numbers. You do not know what the cosine of 1, 2, 3, 4, or 5 is. They bounce around. They're somewhere between -1 and 1, though. And you're raising those to the nth power. Well, if I have a number between -1 and 1, and I'm raising it to the nth power of it is between -1 and 1. So this sort of tells me I can simplify this a little bit by using the squeeze theorem. That may not make sense to you, but let's go ahead and just mention that if it was just a nice simple 1 or -1, doesn't matter to me, over the natural log of n plus 1, then I could tell you as n goes to infinity, if it was just 1 over natural log of n plus 1, as n goes to infinity, that's 1 over infinity, which is 0. So that cosine of n to the nth power is the problem. It is the issue. So I'm going to bound cosine. So let me write that down. Since cos of n is an issue, and I'll put in parentheses, we don't know what it is tending to. It's not that it's indeterminate. It's that the limit as n goes to infinity of the cosine of n just doesn't exist. It just pops around forever and ever. So since we don't know what that limit is tending to, we're going to go ahead and bound it. I'm supposed to say. Well, we know that the cosine of n, no matter what, is always between -1 and 1. And so what I'll do is I'll raise both sides, or all three sides, to the nth power. So this implies -1 to the nth is less than or equal to the nth power of the cosine, which is less than or equal to 1 to the nth. By the way, that's just 1. So I happen to know that the nth power of the cosine is between -1 to the nth and 1. Now, here's the problem. -1 to the nth, that just depends. It could be -1, it could be 1. But I know in the worst case scenario, it's going to be a -1. So I'm going to say in the worst case scenario, I know that's going to be a -1. I do get it that it can climb up to a +1 because -1 squared is a +1. But I don't want the best case scenario. I want the widest interval. So I know that the cosine of n to the nth power is always between -1 and 1, including -1 and including +1. Well, what does that mean about our original function there, or original sequence? Well, if you divide all three sides by the natural log of n plus 1, it's supposed to be an n plus 1, then you get our original sequence, and it has been bounded. So this is what in my Calc 1 class, I will say you need to bound the issue function, and then you need to rebuild the function that you're trying to find the limit of. So we've bounded the function that's an issue, and then we've rebuilt our sequence. But we know that the limit as n goes to infinity of -1, actually, I'll just put it this way, plus or minus 1 over the natural log of n plus 1, we know that will be 0 because, well, it's 1 over the natural log of n plus 1. As n goes to infinity, that's 1 over infinity, which is 0. So I have a sequence in the center bounded by two sequences on the edges, but those sequences on the edges as n goes to infinity will tend to 0. Therefore, the sequence in the middle gets squeezed to 0 as well by the squeeze theorem. Thus, the limit as n goes to infinity of that cosine of n to the nth power over the natural log of n plus 1, that's equal to 0 by, again, the squeeze theorem. And you don't actually have to say squeeze theorem for sequences. You can just say squeeze theorem. That's totally fine. I'm not that much of a stickler, so I'm okay with you just saying by the squeeze theorem. That's a great use of the squeeze theorem. You generally want to use the squeeze theorem if you have a sequence that involves several different styles of functions, and you say to yourself, man, I would totally know what this would tend to as n goes to infinity if this wasn't in the way. And that piece right there, as n goes to infinity, just doesn't exist. Well, then go ahead and bound it if you can. It's generally boundable if you have a sine or a cosine. There's some other oddball ones where it doesn't have to be the sine or cosine, but yeah, generally if it's the sine or a cosine, you can bound it. I'm waiting for any questions, but I haven't seen any. So, all right, then moving forward, determine whether the sequence converges or diverges. If it converges, find the limit. I'm taking I don't know if you noticed, probably didn't, just because there's so much going on, but these examples are using all the theorems I wrote down at the beginning. So we just use a squeeze theorem. We have used one of the theorems that says if the limit of the function converges, then the limit of the sequence converges to the same value. And now we're dealing with this guy right here, which is going to use one of our other theorems you're about to see. So as n goes to infinity, we have something, in fact, I'm going to write it in language. Actually, no, I'm not, because, nope, yeah, I am. As n tends to infinity, 2 to the negative n, this is actually that theorem that we wrote down earlier, that if you have a sequence, some base r raised to the nth power, that will tend to converge to 0 if the base is less than 1 in magnitude. And this one is. It's 1/2. 1/2 to very large powers tends to 0. So we know that this will tend to 0. But unfortunately, this cosine of n pi, it's not that it wiggles all over the place. Actually, this ends up becoming something very interesting. For n equals 1, it's a -1. For n equals 2, it's cosine of 2 pi, which is +1. For n equals 3, it becomes cosine of 3 pi, which is a -1. For n equals 4, it becomes a cosine of 4 pi, which is a +1. So this jumps back and forth between plus and -1. And as n goes to infinity, that means it just does not exist. So you have the product of two sequences, one of which tends to 0 as n goes to infinity, the other of which tends to not become anything finite. It just bounces back and forth between plus or -1. Still totally doable. Because you now know you have a piece of this that does not exist, we're going to do what we just did. We're going to bound that piece. So let's bound the issue, basically. The DNE issue. So let's see, the DNE issue is the cosine of n pi. And we know that the cosine of n pi is going to pop back and forth between 1 and -1. So I'm just going to write that the cosine of n pi is always between -1 and 1. Yes, I know it's either -1 or 1, but bounding, you don't really care about that it only is the edges. You're just trying to say, listen, it's always between these values. In fact, I don't know if your Calc 1 teacher ever taught you this, but when you're using the squeeze theorem, you don't have to be so tight with your restrictions. You could say, you know what, the cosine's between -10 and 10. It is true. It is between -10 and 10. It's not going to change whether our overall limit converges or does not converge. So that's just an interesting little side note. Anyhow, we've bounded the DNE issue. Now let's rebuild. Rebuild the sequence. Remember, our sequence was 2 to the -nth times the cosine of n pi. So I'll multiply all three sides of this by 2 to the -nth. All right. Now I have our sequence. It's bounded on the left and the right by other sequences, or bounded above and below by other sequences, whatever you want to say. And we happen to know that the limit as n goes to infinity of plus or minus 2 to the -nth is the same thing as the limit as n goes to infinity of plus or minus 1/2 to the nth. And we have a theorem we just wrote down, well, several pages ago, probably. Is it this one? Yeah. We have this theorem right here that tells us if you have some sequence, some base to the nth power, it will converge to 0 if that base is between -1 and 1. So that 1/2 to the nth power will converge to 0. Let me go ahead and hop back. So this will converge to 0. Since both the lower and upper edges of this tend to 0, the center must be squeezed to tending to 0 as well. So thus, the limit as n tends to infinity of 2 to the negative nth times the cosine of n pi must equal 0. Again, this is by the squeeze theorem. That squeeze theorem ends up being super powerful for us as we move forward in calculus. You'll experience it in Calc 3 as well. So it is actually a continuously appearing theorem. How's that? So hopefully so far this as a review is not so terrible. Now, I'm just looking at the time and I'm looking at this example. Let me see if I have, yeah. So looking at the time, we don't have enough time for this example right now today. So what we'll do is we'll exit a little early today just so that we have more time to talk about this example when we pop back in on Wednesday. So we'll be done. We're done for this morning. I have office hours in 14 minutes. And let's see, just remember that you have, you obviously remember you have homework due tonight, study up for your exam, all that fun stuff. Yeah. So I'll see you in about 13 minutes for office hours. And I'm going to log out on this machine because my computer's weird, but I'll keep on my laptop. So I'll be back in a few minutes. All right. Have a wonderful day. If you're not in office hours, be safe and yeah, enjoy the day. Study hard.